So I'm going to talk a little bit about measurement. So we talk an awful lot about how big the universe is, but an interesting question in its own right is how on earth do we know how big the universe is? To get us started, I'm just going to show a little video. This is done by colleagues at Swinburne University, and it just shows a little bit about how big the universe really is. Does anybody feel small? So obviously there's a lot of different measurements that have to go into producing a film like that demonstrates just how big the universe really is. And I'm going to focus just on two measurements, the very first two measurements we really have to make in order to start to build up that picture. And that is the size of the Earth and the distance to the Sun. These are, seemingly, astronomers rattle these numbers off all the time without even thinking, but it's not trivial to measure these things. Surprisingly, though, the diameter of the Earth was measured very accurately by the ancient Greeks. This is Eratosthenes. He was, on the left. He, among other things, was the director of the library at Alexandria, which is now lost. And he measured the distance the diameter of the Earth. And the way he did that, he knew that on a particular day of the year, the summer solstice, in fact, that the sun shone down a particular well in Egypt. And he also knew that on the same day of the year, the sun cast a shadow from a pole that was pointing straight up and down in Alexandria in Greece. And he knew also, because people could walk, how far it was between these two places. It turns out that just using geometry, which is what the Greeks were exceptionally good at, they invented it after all, he could then work out the diameter of the Earth. And he got an answer that was very close to the right answer. In fact, these days, we're not sure how accurately he knew the diameter of the Earth because we actually don't know exactly how big the unit of measure he used was. And there's some disagreement about what exactly the size of the unit of a measure called a stadia was. That allowed us to measure the diameter of the Earth, which is the very first thing you need if you want to measure the diameter or the distance to anything beyond the Earth. And he did that in 320 BC, so quite a long time ago. It took a long time before we could make the next steps, which was to measure the distance to the Sun. 320 BC, he measured the diameter of the Earth. Ptolemy, just after the birth of Christ, came up with a model for the solar system that put the Earth at the center. And this actually formed a roadblock for understanding the distance to the Sun. And so it wasn't until Copernicus, 1400 years later, completely shook up the scientific establishment as part of what was called the scientific revolution and pointed out that actually a whole lot of things made a lot more sense if you put the Sun at the center of the universe, at the center of the solar system, instead of the Earth. And he was part of this whole rediscovery of the ancient Greeks and all of their knowledge, which continued for several hundred years afterwards. This person, Johannes Kepler, who lived about 100 years later, a little less, actually took the next step. He worked out very accurately what the orbits of all of the planets were. And one of the things that he realized when he worked out those orbits is that very occasionally either Venus or Mercury would pass in front of the Sun. This is called a transit of Venus or a transit of Mercury. And he actually gave an admonition to all of his colleagues that said, you must go and observe the transit of these two planets because they will be very important for understanding how our solar system is constructed. This is his admonition. So the very next eclipse of Venus, I'm actually going to focus on Venus, and you'll see why in a minute. The very next transit of Venus happened just a few years after he published this admonition in 1631. And as far as we know, no one saw it. I'm going to show several of these. What you see is actually a map showing where the transit of Venus is visible from. So of course, because the Earth is round and the transit of Venus only usually takes a matter of an hour or two or less, not everyone can see it, obviously. So what you see is that the lightest area you can see most of it, and then in the gray area you can see some, and in the black area you can't see any of it. In 1639 was the next transit of Venus. They tend to come in pairs. And it was observed by James Gregory. Oh, no, sorry. It was not observed by James Gregory because he would have been 1 year old. Those two eclipses were observed. The second eclipse was observed by one person, but at the time there was no method that allowed him to do anything useful with his data. It took this person, James Gregory, to propose a method by which you could use the transit of Venus to compute the distance to the Sun, to measure the distance to the Sun. Ironically, this was picked up by Edmund Halley of the comet fame, and actually now the method is entirely attributed to Halley. So if you want to get your research stolen, if you want to get it noticed, it helps to have someone famous point it out, but at the same time you may be lost to the history. So this is the idea of the measurement. Basically, you have two different observers on the Earth in different places on the Earth, and both of them watch the transit of Venus across the disk of the Sun. But because each of those observers has a very slightly different perspective on the Sun, they see Venus cross a slightly different part of the disk of the Sun. And if you work out the difference, so you can measure the time that it takes for Venus to transit. If you work out the distance between those two times, then you can work out the angle, and then it's just geometry, assuming, of course, that you know the size of the Earth. So, of course, we know the size of the Earth. That was worked out 2,000 years ago. Now we just have to go and make these two very accurate measurements. I'm just showing that a little more carefully. So the next time that Venus transited was 1761. And this time, everyone was really excited. The astronomical community was very excited about being able to measure the distance to the Sun. And so something like 100 astronomers all around the world tried to go and measure the transit of Venus from different locations so that we could make this measurement. And I'll go through a couple of them. The first pair, Jeremiah Dixon and Charles Mason. If anyone in the audience is from the US, you will know these two because they surveyed a very famous border between the northern United States and what at one point was the Confederate States of America. But they also went and measured the transit of Venus. However, during this time, the 7 Years' War was happening between France and Great Britain. So this made it very difficult. They actually went aboard the HMS Seahorse to be transported to somewhere in the Indian Ocean. I can't remember actually where they were headed now. And they didn't get very far before a French warship appeared and started attacking them. And they very nearly were captured, except that in the nick of time, another Royal Navy ship appeared on the horizon and scared the French ship away. They sailed back and they said, "We're not going to do this. We won't do this." The Royal Society, who had sent them, actually threatened to sue them if they didn't go. And eventually they capitulated and sailed to make their measurement. The next measurement was made by this person. This person had a very famous story, so this was on the French side of the conflict. I will try and pronounce Yom Vision's name. I could pronounce the whole thing, but I'm going to not try. He had a very interesting story. So he also sailed. He was going to go to Pondicherry in India to observe the transit. He sailed in March 1760, a whole year before the transit. He sailed around the Cape of Good Hope. He was stranded on the French island of Mauritius at the time. It wasn't called Mauritius at the time, the Isle of France. And he was stranded there because of the war, waiting for a ship that could carry him to India. And it took almost a year to find a ship that would take him. So in June 1761, just a month or so before the transit, he left finally to go to India to observe the transit. And he sailed, and when they got to Pondicherry, it turned out that the British had taken control of it, and he couldn't land. So he turned around and sailed back, and unfortunately he watched the transit of Venus while aboard the ship. Unfortunately, while you're on a ship, you can't make the accurate measurements that he needed to make, so the time was essentially wasted. He went back to Mauritius, and he decided that since he was already halfway around the world, he might as well wait the next 8 years to see the next transit of Venus. So he spent some time mapping Madagascar, sailing around the Indian Ocean, and eventually he decided that he would go to the Philippines to see the next transit of Venus. There was no war on now, the 7 Years' War ended, so he sailed for the Philippines. However, the Spaniards, who had control of the place in the Philippines that he wanted to land, wouldn't let him land. So somewhat disgustedly, he turned around, and this time he was actually able to go to Pondicherry in India, which was now back in French hands. And when he got there, he set up all of his instruments, and he was all ready to go. Everything was ready. He had beautiful weather right up until the day of the transit, and on the morning he woke up, it was cloudy, and he didn't see it. When he got back to France, he found that he had been declared dead. His wife had left him, and it took him quite some time just to recover his fortune. He eventually remarried and lived a happy 21 years afterwards. After the 1761 transit, a person named James Short, among others, sat down to try and to compare all of these measurements that had been made in order to work out the distance to the sun. You have to have the measurements from 2 different places in order to measure the distance. And he came up with this magic number, 152 million kilometers. Now, this was a reasonably good estimate. He thought long and hard about it, and it's actually not a bad estimate. Unfortunately, he wasn't the only one. Various other people used the same data and came up with numbers all over the board. And so unfortunately, astronomers decided that we had not accurately measured the distance to Venus, to the sun or to Venus, and therefore we had to try again. So that left the 1769 transit of Venus. The best place to observe the 1769 transit was from the South Pacific, or somewhere in the Pacific. So the Royal Society of Great Britain decided that they would send someone there to observe it. Now, like all good scientists, when you have a science project you want to do, the first thing you do is apply for a government grant. So they went to King George III and asked for money to fund an expedition to the South Pacific. Now, for reasons I'll explain in a moment, King George was very eager to send an expedition to the South Pacific, and so he very happily gave them the money to go. It cost them about £2,800 to buy a ship, and they also had to choose a captain. Now, James Cook actually was not a commissioned officer at the time, but he was the most suited for the job. So they made him a lieutenant in the Royal Navy and put him in command of what at first was the Earl of Pembroke, but was later renamed the HMS Endeavor. They spent £2,800 buying the Earl of Pembroke, and then £2,600 completely refurbishing the ship to make it the Endeavor and to make it suitable for the voyage that they wanted to go on. James Cook sailed to Tahiti, and he and 3 of his assistants observed the transit of Venus. They were lucky enough to have beautiful weather on the day, and he was actually so worried about the possibility of cloud that he actually had his assistants observe in different places. So they were actually spread out across the island to make the measurements. The one thing that they had not expected, these are actually the drawings from that Captain Cook made, was this thing called the black drop effect. So you'll see that Venus gets a little blurred when it gets near the edge of the sun, and it made it difficult to measure the exact time that Venus contacted the surface or the edge of the sun's disk. But nonetheless, he made his measurements, and once he'd finished making his measurements and packed everything up, he opened sealed orders from the Admiralty. And now we find out why King George was so eager to fund this expedition. The orders instructed him to sail south and search for a continent, Terra Incognita Australis, and map it out and claim it for the British Crown. And of course, we are now sitting in Australia. So here is Captain Cook standing in Botany Bay. He actually didn't originally name it Botany Bay. It was renamed after he sailed away. Standing in Botany Bay, meeting with the the locals and claiming the land for Great Britain. After everyone got back to Great Britain, they were able to measure, again, collate all of the data from all the different expeditions and again try and measure the distance to the sun. So at the top is that estimate from James Short that was made after the 1761 transit. There were many people, again, that looked at the data and analyzed it for the 1769 eclipse, and they actually combined both sets of eclipses so they could, transits, so they could do even better. And Jérôme Lalonde's estimate, I'm sure I butchered that, was 153 million kilometers. Now, that was actually fairly, he had an error of only about 1 million kilometers on that measurement, so he was reasonably confident, and other people got the same answer this time, or reasonably close. And so astronomers accepted that we had a very good estimate for the distance to the sun. It was actually measured again in the two lots of eclipses in the 1800s, and they basically found the same answer. Now, how many people here went and saw the transit of Venus a few years ago? A few hands. Good, good. There was actually a citizen science initiative. If you had an app on your iPhone, you could watch the transit of Venus through your telescope, and you could tap at the appropriate time when the Venus was entirely within the disk, and then again when it left the disk, and they were going to remeasure the distance to the sun using that data. I don't actually know how close they came. Don't actually know how close they came, but what we do know now is that we actually, since about the 1960s, can measure the distance to the sun using radar. And this gives us so accurate an estimate that we actually, it's this number, but the error on this number, the accuracy with which we can use the radar to measure the distance, is about 3 meters. In fact, it's so accurate that we can watch the distance between the Earth and the sun change, and we now know that it does change continuously over time. Now, there we go, 0.03 kilometers error, so just about 3 meters, which is pretty impressive considering it's 149 million kilometers to the sun. Now, I mentioned, if anybody's actually read the little abstract I wrote, which probably haven't, I mentioned that I'll make a comment about how we actually know the mass of the sun more accurately in kilometers than we know it in kilograms. So I should explain that comment. This is the slightly more technical bit of the talk. So the way that we can measure the mass of the sun is actually related to the way we measure the distance. So this little formula tells us the distance to the sun. Depends on Newton's constant. The mass of the sun, which is what we want to know, is big M. The distance to the sun, which we've now measured either with radar or originally with the transit of Venus observations, and the length of a year. It turns out that we can measure the length of a year to within about a second, and we can, as I've pointed out, measure the distance to the sun within about a couple of meters. What we don't know is how accurate the value of this thing called G, the gravitational constant, is. It's actually terribly inaccurate because it's terribly difficult to measure. It tells also how we know the mass of the Earth. So we actually don't know the mass of the Earth very well either. Anyways, if you work it out, what you find is that the accuracy with which the most accurate that we know the mass of the sun is 240 million billion kilograms. So it could be more or less by that amount quite easily, and we would still have the right answer. So we know the distance, and we can measure in some weird units the mass of the sun to within a couple of meters, but in kilograms we can't get anywhere near close. Thank you. It's actually a pretty small percentage of the mass of the sun. It works out to a few hundredths of a percent, I believe. Something I didn't mention is that I've explained how we measured the diameter of the Earth and how we used that diameter of the Earth to then measure the distance to the sun. These are actually the very first steps in something we call the distance ladder, the cosmic distance ladder. The next step is actually to measure the distance to the nearest stars. And for that, we have to know the distance to the sun. This process repeats over and over and over again until we build up this whole picture of the universe. Any other questions?